Okay, so like I said, what we're going to do is we're going to be starting the semester with a little algebra review, because we're going to use a whole lot of algebra this semester, and especially working with radicals. We've been working with radicals so far this year, and you've been working with them somewhat, but we need to kind of formalize what's expected with them. In fact, you saw some stuff come up probably on the exam and just before the exam as well, but we're going to spend, like I say, just a day here looking at this and reminding how this stuff works from Algebra 1. So in most cases of geometry, we do not simply decimally approximate radicals. So if we get something like square root of 72, I don't just put down that that is about 8.6 or whatever that would be, 8.5, somewhere around there. We actually write things in lowest radical form. And especially in this chapter where we start working with Pythagorean theorem, a lot of times we're going to get answers that are in terms of radicals. We're going to have to work with radicals through the process of the problem. And so that's kind of what we're going to talk about today, is how to express final answers, how to work with radicals, things like that. The step-by-step process for simplifying radicals, again, this is something we've gone over a few times, at least in my sections. You probably did where you had it, had geometry as well, is pretty simple. First step, is a number under the radical a perfect square? Like 16 or 25. By perfect squares, those are the numbers I'm talking about. If it is, yes, and we just simplify it and we're done. Problem is solved. So if I get like square root of 16, that's 4. Done. I don't have to continue to take the square root because it's already been solved out. Is there a perfect square that is a factor of the number under the radical? And here's where it starts getting interesting. There are lots of numbers that are factors of numbers under radical. Say for square root of 10. So let's say we had square root of 10. There are factors of 10 besides 1 and 10. 2 and 5 work. But neither 2 nor 5 are perfect squares. So factoring into square root of 2 and square root of 5 does not help me at all. So I'm only interested if I have perfect square factors. So we have to be a little bit careful with that, checking to make sure at least one of the factors is a perfect square. If there are perfect square factors, we go to step 3. It says find the largest perfect square that is a factor of the number of the radical. And the process for doing that is pretty simple. Start by dividing the number under the radical by 2. Is that number a perfect square? If not, then we start testing the perfect squares less than whatever that figure is. And we'll do some examples of how that works in just a minute. So we try each perfect square less than that number, starting with the largest and moving down the list until you find one that works. And finally, rewrite the radical as a product of 2 radicals made up from the factors from step 2. The first solution should be the perfect square. The second should be the other number, and solve the perfect square. So if you're the type of person who likes written step-by-step instructions, that's a great page. Now, a lot of people don't like written step-by-step instructions. A lot of people like examples. And that's where we're going to head next. Square root of 90. Step 1, 90 is not a perfect square. So I start looking for perfect squares that are factors of 90. I'm not sure if there are any perfect squares that are factors of 90 or which one they are. So I start by taking half of 90 as 45. Why? Because that would be the easiest factoring we could have. If 45 was a perfect square, we'd be golden at square root of 45 times square root of 2. But again, that doesn't help me. 45 is not a perfect square. I do keep in my mind, and a lot of people keep on a piece of paper, a list of perfect squares. That list of perfect squares looks like this. 1, 4, 9. Those are the first 15 perfect squares. That's a list you should be familiar with, or at least be able to recreate pretty easily. And that's an easy list to create, right? I mean, if you get stuck, you get out your calculator, go 2 times 2 equals, 3 times 3 equals, right? Or 2 squared equals, 3 squared equals. So you can always recreate that list. So I start, 45 is my starting point. 45 would be right about here. And I start testing numbers less than 45 to see if they go evenly into 90. So I start checking. 36 is the first one. 36 is not a factor of 90. How did I know that? I probably took out my calculator, I did 90 divided by 36, and see if I get a whole number. If I do, fantastic. If I don't, continue on. Next down the list is 25. We check 25, does not go evenly into 90. Next, 16. 16 does not go evenly into 90. Next, we check 9. So we're just working our kind of guess and check, working our way down the list. Or in this case, up the list. 9 is a factor of 90 10 times, so I rewrite my radical. Square root of 9 times the square root of 10. Or square root of 9 times 10, because 9 times 10 is 90. Now, very intentionally, I put the perfect square one first. I don't put the larger one first, I don't put the smaller one first. I put the one that's perfect square first. Now, since rules for multiplying radicals are nice, I can break that up. Square root of 9 times 10 is the square root of 9 times the square root of 10. But the square root of 9 is the one that simplifies. It's 3. So I simplify that out, and I often do this. Actually, you'll see me do this when I'm doing that. I X that out to indicate to myself I am simplifying that number. Square root of 10 does not simplify. 3 root 10, that's my simplified solution. We're done. Step by step. And we don't write down all of the different guess and checks that we do. I did here just so you could kind of see the process in action. But that's how we simplify radicals. And like I say, we've been doing this kind of for a while, so some of you have gotten fairly good at it. Some of you, it's still a point for improvement. So that's why we're spending a little extra time. So let's try a few of these. Square root of 45 is 45, and I'm going to make my little list of perfect squares again. We can keep going on. Okay. Is 45 a perfect square? No, 45 is not on our list. What's half of 45? That'd be 22 and a half, so about 22. That's not, it's 22 and a half, obviously, it's odd. It's not going to be a perfect square, but it tells us where to start. I'm not going to check to see if any of these numbers down here because 22 is halfway, I'm not going to check any of these numbers to see if they're factors because they aren't. They can't be. So I work my way up. Does 16 go evenly into 45? Nope. Does 9? Oh, yeah. Square root of 45 is the square root of 9 times 5, because 9 times 5 is 45. That's square root of 9 times the square root of 5. Square root of 9 solves out. That becomes a 3 root 5. So when it comes to showing your work, that's basically what I would expect to see. Now, I still get some people who want to swap these. They do 5 root 3 instead of 3 root 5. Be careful about that. You got to take your time. Square root of 120. 120 is not on my perfect square list. It's so close. 121 is, but not quite. So I'm going to start with half of 120, which would be 60. 60 would be right about there, so we're going to work our way up from there. And see which of those goes into 120. 49, does that go evenly into 120? How about 36? No. 25? No, that's pretty easy. 16. Does 16 go evenly into 120? See, a lot of people going, I don't know. Does it? How could you check it easily? What should you probably have? What would be helpful to have out right now? Anybody? I could pick on Milton.
Calculator.
Yeah. She looks like she's not paying attention, but I know that she is. So if you don't have one with you, you might want to make sure you carry one. By the way, it also bears mentioning that in this chapter you will definitely need a scientific calculator. And I see most everyone who's pulling one out has a scientific calculator. But that means the calculator has sine, cosine, and tangent on it because we will be doing some trig in this unit. You're going to learn the basics of trigonometry in this unit in the next few weeks. Next couple weeks. It's fun. So does 16 go evenly into 120? No, it does not, sadly. How about 9? 9 does not. 4. Yeah, 4 and 30 do. So 4 is the number I'm looking for. So that's square root of 4 times square root of 30. Square root of 4 is 2. And I know that nothing is going to go into 30 because, again, I've tried all those larger numbers. Because factors of 30 are like 2 and 15, not perfect squares. 3 and 10, not perfect squares. 6 and 5, not perfect squares. So nothing goes in there. Let's go to 32. 32 is not on my list. It is not a perfect square, but what's half of 32? Is 16 a perfect square? Yes, it is. 16 times 2, square root of 16 is... Now, here's a pretty common mistake that people make. They get the square root of 16 and they get 4, and then they go, oh, 4 is a perfect square. But this 4 is outside the radical already. So we don't have to simplify. Once it's out, it's out. We don't have to keep simplifying it. So that's easy. Square root of 333. Ouch. Not a perfect square. Half of 333 is not going to be a perfect square. Are there any perfect squares that you can see right away that go into 333? We can work our way down if we want. I mean, half of 333 would be what? 166. Okay, so 144, is that going to go in evenly? How about 121? No. 100 doesn't. 81? Not quite, no. 64 does not, it's even. 49, does 49 go evenly into 333? No. 36 does not. Does 25? No, obviously not. 16. Working our way down. 9. How many times does 9 go into 333? 37? Square root of 9 is 3. Now, I probably could have started very quickly with the square root of 9 if I wanted to, because 3 plus 3 plus 3 is 9, isn't it? If the digits of a number add up to a number divisible by 9, that number is divisible by 9. Same trick works with 3. So if I get a number like, if I get a number like 2,718, and I want to know if that number is divisible by 9, well, I take 2 plus 7 plus 1 plus 8. That's, if I add those, that's 18. 18 is divisible by 9, so 2,718 is divisible by 9. So would 2871, or any variation of that, any number that, or 8712. All 4 digits, when I add those digits together, the sum is divisible by 9, therefore that number is divisible by 9. Yeah. Yeah, that makes it a little more obvious, but that's because I made it up quickly off the top of my head. So anyway, yeah, again, you can make that work. It's a little trick we can work with. If the sum is divisible by 9, the number is divisible by 9. That's a 9 rule. It also works for 3, but that's about it. Now, that part of simplifying radicals is what we were doing all year. And most, I'd say 2/3 of the people, at least in my class, were getting pretty decent at that. and about a third we're still struggling. But there are a couple other things we're going to do with radicals in this chapter that we have to be prepared for. First is squaring them. Supposed to be a square root symbol there. Okay. Squaring radicals. Our general rule we're working with here is that the square root of any number squared is that number. We could also say the square root of n squared is n. Either way. Square root and squaring are opposite functions. They're inverse functions of each other. They cancel each other out. So that's our basic rule. So if I have something like the square root of 43 and I need to square it, that's easy. That's just 43. That's all it takes. And it doesn't make a difference if the square root is outside or it's the square root of 43, like that. It works the same way. So that's not bad. What gets interesting is when we start dealing with something like 3 times the square root of 10 squared. We get a product squared. More interesting, and what we aren't going to get into so much in geometry, but you did in algebra, is if you have things like 3 plus the square root of 10 squared. That's more of an algebra 2 type thing, where we start foiling things out with radicals. And yeah, that would be a FOIL long multiplication, first outside, inside, last thing. We would have to rewrite that as 3 plus root 10 times 3 plus root 10, and then multiply that out. We aren't going to do that in here so much, okay? That's not where we're going. So relax. If you're panicking a little bit at seeing that, if you're getting hyperventilating just a little bit, you can stop. It's okay. Deep breath. Good air in. You guys are like totally flat and quiet today. It's because Bella's not here, isn't it? And you can't yell across the room at her. It's very strange. Okay. All right, so how do we do that? Well, our rule is simply this. A times b squared is a squared times b squared. So if I have to square 3 times the square root of 10, I square each component of that. 3 squared times square root of 10 squared. 3 squared is easy. What's 3 squared? 9. Square root of 10 squared itself is easy. It is 10. Oh, 9 times 10, I can do that. 90. So if I square 3 root 10, 3 root 10 squared is 90. Now, where is that going to come in handy? It's not hard to imagine. It's Pythagorean theorem. What if I told you that we were doing Pythagorean theorem, which we're going to do in a couple days, but you already know, so that makes life easier, and this side of the triangle was 3 root 10. And I had a side here that was 7 or something like that, and you had to find the third side. We're going to have to square something like 3 root 10, aren't we? We're going to have to square that out. And it usually comes out nice numbers like that, like 90. So, and by the way, you may notice that earlier example, square root of 90 was 3 root 10. It's consistent. So let's practice this one a little more. In fact, why don't you get out a piece of paper and a pencil and practice these. See what you can do with them. That means you got to stay awake a little bit. There we go. Just a piece of scratch paper and a pencil, and work on squaring these out. I'll start the first one for you here, and I'll see how you do it. Let's just try a couple of these. Just be careful. It's square root of 5 squared. This is 5. Don't lose your square root signs. Okay, got that first one. Good. Don't just put in your calculator. Do it. What's the square root of 5 squared going to be? 5. Just 5, right? Because that's the opposite function thing. And 4 times 5 you can do. Right. You definitely got it. Good. Careful. 7, not 7 times 2, 7 squared. It's okay. It happens. Good. Okay, now we're getting something. You getting there. Not doing it. All right. Some of you are doing pretty good with it. Some are still struggling a little bit. Some are trying to punch it in your calculator and see if you can get your calculator to do it for you, which, if you're pretty creative, you probably can, but in the end, you're going to need to know how to do these types of calculations, so you better get used to doing it manually. And you're going to have to show your work on your homework anyway, so if all you do is punch in your calculator and get an answer, that's probably not going to be sufficient to your homework. So get used to the process. Notice what I did. I start by rewriting the problem in expanded form. Then I actually do it. 2 squared is 4. Square root of 5 squared is 5. I keep that multiplication there. 4 times 5 is 20. 4 root 11 squared. Again, that's going to be 4 squared times square root of 11 squared. I write out each step. And those who had me last semester got sick and tired of me hearing me say it, but I do say it a lot. The more steps you show, the fewer mistakes you're going to make. People who try to shortcut often make a lot of errors. So 4 squared is 16. Square root of 11 squared is just times 11. Now, 16 times 11, that can be a little tricky to do without a calculator, but not so bad, because I'll show you how I do it. I don't have 16 times 11 memorized, but I know that's 16 times 10 plus 1, because 10 plus 1 is 11. And I can do 16 times 10 is 160, and 16 times 1 is 16. Oh, easy. That's how we break it up using mental math. That's how we take bigger numbers like that and work with them. And break them up. 7 root 2 squared. Again, 7 squared times the square root of 2 squared. What I was seeing walking around on problems like this, a couple things. People not writing the square root symbol down because, by gosh, it's just too darn hard to write that symbol. Do not ever leave the symbol off if it's a square root. You're going to forget to put it back. And it's going to create a nightmare for you. You don't want it. 7 squared, not 7 times 2, that's 49. You get a lot of people who do 14 there. That's a very common mistake. Just be aware of it and be careful. Squaring is not the same as times 2. Square root is not the same as divide by 2. Unless the number being squared or square rooted is 2. or 4 square roots. So square root of 2 squared is just 2. So 49 times 2 is 98. And one more time, 8 squared times the square root of 6 squared. 8 squared is 64. Square root of 6 squared is 6. And again, I don't have 64 times 6 even close to memorized, but I know 6 times 6 is 36, so that's 360. 6 times 4 is 24, so that's 384. So if you're saying, well, how does he do that without a calculator in his head, or without a calculator, is I split it up. I take the big problem, I turn it into easier problems, just like I did here mentally. 6 times 60, that's easy. 6 times 4, pretty easy. Because 6 times 60 is just 6 times 6 plus a 0 to it. So those are the 4 solutions. If you got those 4 solutions, fantastic. If you didn't, well, we'll be practicing some more tonight. You get some more chance to practice with that. But again, this is what I would expect to see for work on these types of problems. Show it expanded, actually do each step, and then the solution. Maybe not, you wouldn't have to show that necessarily. And as is traditional, especially in a worksheet, if there's an answer blank, circle your final answer so I can find it, or on a test, or put a box around it, either way. But I want to be able to identify what your final answer is. Last thing we're going to have to do, rationalizing radical expressions. One of our rules, at least to this point in math, is that we do not want radicals in the denominator of our fraction. Now, when I have a fraction, I can always reduce, but I can only reduce things under radicals with things under radicals. This would be the same thing as the square root of 8 over 32, which reduces to 1/4. So reducing makes my life easier. Just plain old fraction, reducing. Then I can split that up. It's the square root of 1 over the square root of 4. And I simplify as best I can. 1/2. Now technically, it's positive or negative 1/2, but for our sake, we'll just leave it this way. So that's a relatively easy one. Square root of 8 over 32 reduces to 1 is actually 1/2. That's all there is to it. Some get more complicated, though. What if I have square root of 3/7? How do I handle that? Well, again, we split it up. It doesn't reduce, so square root of 3 over square root of 7. And now this is where it gets interesting. Because I'm not allowed to keep a radical in the denominator. They don't simplify. I have to what's called rationalize this fraction. And that means I have to multiply it by another fraction that has a value of 1. So if I multiply by anything but 1, I'm going to change its value. But when I multiply a number by 1, it keeps the same value, right? 8 times 1 is 1. Or 8, excuse me. 52 times 1 is 52. Multiplying a number by 1 does not change its value. I can express 1 however I want. I could say 1 as 1 over 1. I could say 1 is 5 over 5. I could say 1 is pi over pi. I mean, I could put any value I want there. As long as it's the same top and bottom, it still equals 1, right? So I'm going to choose one that makes my life easier, and that's the square root of 7 over the square root of 7. That's how I'm going to express 1. Why? Because when I multiply the denominator now, I get square root of 7 times square root of 7, which would be square root of 49, which is just 7. And square root of 3 times square root of 7 would be the square root of 21. And we've simplified that. We've rationalized that fraction. So there's what we do and why we do it that way. Now notice I can't reduce the 21 and the 7. This is under a radical. This is outside a radical. They do not reduce and cancel with each other. They don't associate with each other, the ones that are inside and the ones that are outside. Square root of 5/15. First question we ask, can I reduce that? Does 5 over 15 reduce? Sure does. What's it going to reduce to? 5 over 15. Yeah. 1/3. That's the square root of 1 over the square root of 3. The square root of 1 does simplify. That's just 1 over the square root of 3. But I'm still left with that square root in the denominator, so I'm going to rationalize it. How am I going to write my 1 this time? What over what? 7 over 7? What is going to be top and bottom here? What do you think? 3 over 3. Well, let's see what happens. Oh, there we go. Big difference. Without the square root, it wouldn't have worked very well, but this way it does. 1 times the square root of 3 is the square root of 3. Square root of 3 times square root of 3 is just 3. Solves out. No more radical in the denominator. We're solved. Or simplified. Square root of 3 over 3. Square root of 2 over 11 does not simplify, so what are we going to multiply top and bottom by? Square root of 11. Square root of 2 times square root of 11 is square root of 22. Square root of 11 times square root of 11 would be the square root of 121. But square root of 121 is just 11. Can I reduce that? No. So multiplying, simplifying, those are all the things that we're working on. All these little different tricks with radicals. That's what we're after just today. And I've got a worksheet for you. I know you're excited. Answers are on the last page, so again, be sure you're showing your work, because I'm not just giving you this so you can copy the answers off the back page that I already wrote down. There you go. Mm-hmm. All right, and for those who aren't familiar, real quick, my web page always has the assignments on it as well. See if it's going to come up. If you want to keep up with what's going on, what our schedule is, it's right there. What? Can you throw it all out? Well, we'll still be using it, but am I grading it anymore? No.